couple quick announcements before we get started. This is our last seminar of the semester, or our last regular seminar of the semester. Next week we're going to have the student presentations, which are going to be a couple of the capstone presentations for our master's degree in physics. And I haven't gotten the titles and the abstracts for all those talks, but I'm planning on sending those out and just distribute those through the email list and the Facebook page and stuff like that. Also, another thing is this semester we had a sponsorship from United Space Alliance, and so that support is going to help us a lot in the future. So it's going to be more talks like these, more really good speakers, and that's just going to be a continuous thing. And also, if you want to keep information on what we're doing with this sign-in sheet that's going around, if I have your email address, I'll send you emails about what we're doing. Also, check if you're on Facebook, we have a Facebook page on there for UHCO Physics. And we'll just keep any announcements about talks or any of the other things about upcoming courses or other things we're doing in the program through that. So with that, I'm going to introduce our speaker tonight. This is Leonard Cassady, and he's going to be talking about the VASIMR engine, and essentially what he's going to be doing is he's going to be giving an update. I think the last time we had a VASIMR talk at the seminar series about 3 years ago, 3 or 4 years ago. So a lot's happened in that time, and so I'm going to let Leonard fill us in on that.
Thanks a lot. Thanks for having me. Tonight's talk will be about the VASIMR, specifically the VX-200 engine, which stands for the experimental 200 kilowatt engine that we're developing in our facility over in Webster. My talk will start off with some mission scenarios that Astra is good for. And move on to some of the technologies that we've been developing and some of the recent results that we've had. Some of the results are a year and a half old. I guess they're since we were here last. We have a couple of results from the last few weeks. Most of the most interesting results are about 6 weeks in the future, so you guys can check our website in a few weeks. As usual, we're almost there, so the results are a little bit thin, but you'll still like this presentation. Astra Rocket Company is a private corporation. We are a spin-off from NASA in 2005. There was a Space Act agreement which took the ASPL and moved it private so that the electric propulsion research could continue. At that time, NASA pretty much cut all high-power electric propulsion research, and it was just a nice coincidence that we had our own company moving forward. And right now we're moved to a building off NASA. We're fully privately invested. There's no government money helping us right now, and it's been that way for 3 years. You can come and stop by our facility anytime. You can email me and we'll give you a tour. So VASIMR stands for Variable Specific Impulse Magnetoplasma Rocket. This is just a cartoon of what it looks like. Basically, the key is we have a plasma in the center of the rocket that is contained by a magnetic field. We use superconducting magnets to contain the plasma because once you ionize a gas, it sticks to the magnetic field lines and doesn't impact the surface nearly as much as like a chemical rocket. So you start with a neutral gas, usually an inert gas like argon or helium or neon. Any of those work. Right now we're focused on argon because it gives us the specific impulse that's good for low Earth orbit and lunar missions. You inject it in the front end of the rocket, and the first stage is where you just ionize it. So you take RF power and transmit it into the center of the rocket and broadcast it or couple it into the gas. It fully ionizes the propellant, so you get 100% ions coming out into the second stage. Then it goes through a little choke. This is the second magnet here. That kind of condenses the plasma down a little bit. That way that the neutral gas has less of a chance of passing through, and it also separates the two stages of the rocket. Then you have the second stage, which is the RF booster or ICH stage. In that stage, you broadcast more RF power into here. That RF power frequency is the same frequency as the ion gyro frequency. As the ions are moving down the magnetic field line, they are trapped on the magnetic field line and spin around to the charge to field strength ratio. If you hit it with the frequency that's the same as that, the energy just with pretty much 80 to 100% efficiency, gets into the perpendicular energy of the ions, and they spin up, and it's a very efficient way of heating the ions. And then as the magnetic field drops off, because the field expands as you come out of the solenoid, that perpendicular energy is transferred into axial energy through conservation of momentum. And then you have an accelerated plasma. And that's basically how our thruster works.
Lenny?
Yeah.
Is the second antenna a helicon? It sort of looks like it there.
It is not a helicon. This is all we can show you. The keys to our rocket are really the shapes of the antennas and some of the materials and thermal issues on the inside. Those are things we don't want to say too much about. But it's not a helicon antenna, but it does have straps, and it operates in the AM frequency range, hundreds of kilohertz. That's what I can tell you. So just to I just told you about electric propulsion. I'd like to compare it to something everyone here is usually pretty familiar with, chemical propulsion. Everyone's seen the space shuttle take off on TV, and you have your Estes rockets at home. So that's what chemical propulsion is. Basically, you take a fuel and oxidizer, combine them, they react, and you get thrust. The exhaust velocity, which is acceleration of gravity, times the specific impulse. That's what specific impulse is. It's the exhaust velocity divided by acceleration of gravity. So it's pretty low. It's around 450 seconds at best. That's the space shuttle main engine. That's the highest you're going to get for specific impulse. And high thrust, these things are, the smallest ones are around a newton, and the biggest ones, like the space shuttle main engine or the F1 engine, are in the 10 to the 6 newton range. They have a short firing time, mostly because they have a low specific impulse. They burn up the propellant very fast. It's very hard to carry around a lot of propellant for these low ISP rockets. Electric propulsion, the main difference is it has a high specific impulse, 1,000 to 40,000 seconds. So you use a lot less propellant. It has a low thrust, so you have to fire for a lot longer than 10 minutes. You're firing for months to years usually. Non-thrusters usually fire for about a year in their lifetime and a few months for Hall thrusters. But you need to bring along a solar array to keep them going. So it usually takes a few kilowatts of power or slightly less to run the rocket. But the main advantage is it saves propellant. And the easy relation is the rocket equation. You have the initial mass, or the final mass is the exponent of the delta V, which is the characteristic change in velocity for your mission, say you're changing your orbit. And the exhaust velocity, which is, as I said, 10 times basically the specific impulse. So you can see if you change your specific impulse, you get a major savings in propellant. And that's really the key, is you don't need to bring as much propellant to low Earth orbit. So I'm going to start by showing some concrete examples of how you can save propellant. This one is taking cargo to the moon. So when we go to the moon in 15 years or whenever NASA gets there, they're going to have to bring cargo in advance and resupply quite often. We're going to assume that the launcher to bring the cargo to the moon is like an Ares 5. We're going to round the mass to low Earth orbit to 100 metric tons for this study. And we're going to compare from that point on, once you're in low Earth orbit, getting there with chemical rockets, all 450 seconds specific impulse, and then using a VASIMR version to bring stuff from low Earth orbit to low lunar orbit. This is just some pretty NASA pictures of the lander. So the all-cargo flight, this is the Ares 5 computer model. Really, it's more like 180 metric tons of low Earth orbit is what they're planning on now for the Ares 5, but just for the purpose of the study, we're going to use 100 metric tons. The translunar stage, which is just the part in the top, is dominated by the propellant for the chemical propulsion system. And I'll go through the details of how much mass there really is. So basically, this is Earth and this is low Earth orbit, this is the moon and this is low lunar orbit. You want to get from here down to the surface. For this, we're going to use the 450 seconds, which is a pretty optimistic and specific impulse for a chemical rocket. There's the there's the cargo stage, a mass of 100 metric tons. ELI is, of course, translunar insertion. Translunar insertion burn is about 3,000 seconds. That's just a home and transfer burn. And using the rocket equation, you get about 50% of your initial mass in low Earth orbit is left after you do the TLI burn. So you're left 51 metric tons is coasting on the way to the moon. And it takes about 3 days to get there. So you insert yourself into the low Earth orbit, or low lunar orbit, and that's about a delta V of 1,000 meters per second. And you are left with about 22% of your propellant, or of your mass. You discard the stage because you don't need the engine or the tanks anymore. And you're basically, this is the key, you're left with 35 metric tons in low lunar orbit. And as you descend down, which is about 2,000 meters per second further change in velocity, you end up with about 18 metric tons on the surface of the moon. So you start off with 100 and you end up with 18 on the moon. That's not a lot. So I'm going to show you that we can save a decent amount of propellant, or a decent amount of mass. So our idea is to have a VASIMR orbital transfer vehicle. You get rid of that whole big translunar stage with the chemical propulsion system, and you use this. This system can be used many, many times. You launch it into orbit using a smaller vehicle like a Falcon 9, a SpaceX Falcon 9, or a Delta rocket, and it can go back and forth to the moon carrying propellant or carrying cargo 10, 20 times, something like that. Basically, it uses 10 megawatts of input power. These are the solar arrays stored. So this is just after launch. I have a video that shows all of this expanding out. It docks on the front end to the cargo. There's radiators because if you're running 2 megawatts of input power, you're going to have some waste heat from that system. And here's four engines. They're about half a megawatt each. And the mass, which is, for when you do mission studies, you usually put in a mass, and it's 2 kilograms per kilowatt is a specific mass. It has a weak influence on the overall results when you're dealing with cargo, because the cargo is the main part of the mass. The rocket is a small fraction. So here's a cool video of. So these are the 4 VASIMR engines. They're 500 kilowatts each. There's the spacecraft and the docking module with some tanks for the propellant when it comes back from the moon. So the radiators. The launch harness is just for launch to hold the solar arrays in place so they don't shake around during launch. And there's the solar arrays themselves. It's packaged inside a Falcon 9. This is just for, we picked a rocket just for the study. We don't have a contract with Falcon or SpaceX or Falcon 9 or anything, but this is just a good video for sales pitch purposes. So here we go. We're taking off now. You can see it tells it's a Falcon 9 because it has 9 engines on the bottom and it's blue. SpaceX likes blue. So we're going up into low Earth orbit, and hopefully this video goes a little faster. There we go. So now we're in orbit. The fairing comes off, and we start to extend the solar arrays out and drop the launch harness in a second. Go. Solar arrays are extending out from their launch configuration into their extended for deployment. This harness falls away to save weight. And the structure for both this mast and the extension of the solar arrays has been worked on by ATK and NTEC. So this is not just a conceptual design. They've built a small one that's I think about 2 by 4 meters and extended that out. And so this does exist on a small scale. This scale is, of course, about 4 football fields. So it takes a little bit of work to extend it to that size. So here's the radiators deploying. Now the cargo ship is coming, the translunar cargo is coming into low Earth orbit and will dock to our rocket and then be transferred to the moon. Now this mission takes this one takes 6 months. So you have to spiral and slowly increase the altitude of your orbit over 6 months until you get close to lunar orbit, and then you spiral in around the moon to 100 kilometers. This docking mechanism, I don't know if that exists or not. It looks cool. And we transfer some propellant over into our system to account for the return trip from the moon to low Earth orbit. It's about 3 metric tons of propellant. It takes a few weeks to get back from the moon when there's no cargo attached. It just kind of comes back pretty fast. We're counting on there was an Orbital Express mission, I think, that Air Force did, that did transfer of propellant in orbit. And that's based on that. Here it comes flying by. Rockets firing, and we're slowly accelerating towards the moon. Now we're at the moon. It took 6 months.
So how much power do the solar arrays?
2 megawatts.
2 megawatts.
Now,
This is strictly for cargo,
not for humans. Humans, you don't really want to let go through the Van Allen belts for 6 months. So the humans would take the chemical rocket, but without much payload, so their ship would be much smaller, and you wouldn't waste as much propellant with them. But it would take about 3 days, the same as the Apollo missions to get there. And then this is just a pretty ending. Here we go, landing on the moon. So just to summarize the video, the key points, 6 months in transit, and the OTV comes back after it's done and is used 10, 20 more times. But the key is we get down to the surface of the moon and we have 38 metric tons of cargo rather than the 18 from before. So to show the differences in what you would be bringing to the moon, you have the lander, which about 5 metric tons in the chemical, it's 12 metric tons. This is the structure and the propulsion system and everything just to land it on the surface. And then there's 12 metric tons of propellant just for that 2,000 meters per second for landing. And there's 25 metric tons of propellant for the VASIMR mission, I guess at the bottom. So the cargo, 18 metric tons, is pretty small, but it looks much bigger in this one, 38 metric tons. Basically, VASIMR can reduce the number of Ares 5 launches in half because you're bringing twice as much cargo to the moon each time. So we're saving NASA an Ares 5 launch for half of Ares 5 launches, which is a lot of money. No one knows how much that is, but it's probably in the hundreds of millions of dollars. Could be billions. I don't want to say that.
Well, they're saying the shuttle launch is $500 million. So.
Yeah. Hopefully Ares 5 is cheaper than the shuttle launch. Hopefully. All right. So that was the big 2 megawatt big VASIMR rocket. There's also closer near-term potential customers for small lunar payloads. One of them is NASA's Science Mission Directorate. They want to send 1 to 2 pure science missions to the lunar surface every year for the next decade, typically about 300 kilograms. The NASA Exploration Systems Mission Directorate, they want to send some stuff ahead of time for the human missions to test it out, like surface exploration hardware testing and then regolith characterization so you don't land and sink in. The foreign market, there's countries trying to go there just to do science, just to prove that they can do it. India just sent one, I think a month ago, towards the moon. So, yeah, and so we're just going, they don't really care how they get there. So if they want to use a VASIMR to save propellant, they can just get more science per mission. Commercial, of course, there's a Lunar X Prize. People are still trying to get to the moon by 2012, and we help them get there for cheaper. And then there's other science agencies too.
How long would it take to do you said if there's less cargo, you get there quicker. You said that first one was 300. How long would that take?
Well, I'm going to do this slide here. The next 2 slides will be using a smaller VASIMR, 200 kilowatts, and starting off with 4 metric tons. Unfortunately, you can't see the bottom. But you start off with a 200 kilowatt VASIMR, which is what we're working on now, so it's not anything too futuristic. You can get 4 metric tons in low Earth orbit, which is something you can launch with the Falcon 1 into low Earth orbit. So it's not that big of a payload. You can get 735 kilograms to the surface in 6 months. Or no, in 100 days. This one's 100 days. You can get it to the lunar surface in 100 days, and you can have 700 kilograms. So if you wanted to take 300 kilograms, you could do it with 100 kilowatts. Or you could bring 2 payloads on the same mission. This is the details of this. I'll go over when I'm showing you the video. This is transferring from a space station type orbit and spiraling out to get to the moon with a 200 kilowatt VASIMR engine at 5,000 seconds specific impulse and efficiency of 60%. This would be true for any electric propulsion rocket that has the same parameters for specific impulse and efficiency. Basically, it takes quite a while to increase your altitude. We started off at 370 kilometers, and now you're only up to 20,000. As you get further away, of course, you start to make more progress because you're further out of the gravity well. At some point, the mission trajectory will start to change from being in the highly inclined orbit to adjust its inclination to that of the moon. That's when it turned green there, so now it's changing to the moon's inclination. It'll adjust again to try to catch up with the moon so it's phased properly. This wasn't done with an optimal guidance program. This was done kind of by hand by Andrew Elin. So this was his way of phasing it together, and so it was all one big video. Now here comes the moon's trajectory there. Now he's trying to adjust the inclination to the polar orbit around the moon, and now this final color, he's spiraling down to a 100-kilometer polar orbit around the moon. So that took 102 days, and he used 870 kilograms of propellant.
Reason why you chose 0.6?
That's the inclination of the space station. I do not know why you would start off from that inclination. You should start off from Florida's inclination.
Yeah.
From Kennedy.
Well, Ariane launches from the South coast, right? The Lunar or something like that.
Yes.
Which the Soyuz is also just built a facility.
Right. But, yeah, it could be any of those places, but probably not 51.6. So this is just changing the frame of reference to the moon because it's easier to understand what's happening. This is where he's adjusting the inclination to match polar orbit. Or no, that was the phasing. Now he's matching the inclination, and then he'll spiral in. I thought these videos looked pretty cool. It's a pretty easy way of explaining what electric propulsion is. It takes a long time to fire, a few months, but you get there without using much propellant.
Are there any issues associated with the extended duration that you say in orbit from orbital debris?
That's a good question. I do not really know the answer to that. It's no more than it is for space station. I don't know. I don't think it's better.
Except your solar arrays are 20,000.
Our solar arrays are huge.
Catching bits.
The type of solar arrays that we have, or what we intend to use, are actually a very narrow strip that's the semiconductor. There's a huge area that's just this graphite, I think, semiconductor. But we use a mirror, a lens, to shine the light down into a narrow region where the power is actually generated. So most of it's just for heat. It just dissipates the waste heat. The part that's actually generating electricity is very small, so the odds of hitting it are a few percent. Rather than most solar arrays, it's 100%. You hit it, you're going to probably lose a solar cell. With us, we have maybe, I think it's 5% of the area is actually collecting energy. So to put this also into context, there are more than one kind of electric propulsion device out there, and they do exist. The ion thrusters have been flown up to 5 kilowatts. They are 70 to 80% efficient, and they can operate for up to 3 years. About 9,000 hours is about a year. Two examples, well, the 30,000 hours was done in a lab. In space, they've gone up to about 10,000 hours. The ZIPS thruster is used commonly on Boeing satellites for geosynchronous. They transfer them to geosynchronous satellite, and they use north-south station keeping. And there's over 50 satellites with those on it. The N-Star was a primary propulsion system for Deep Space One. There's been ground-tested versions up to 30 kilowatts that are very efficient, 80% efficient. And their HIPAP is done by Glenn, and Nexus was done by JPL. I think these programs were about a few years ago, along with VASIMR. These are really good thrusters in this range, the 5 to 30 kilowatt range. But their thrust density is limited. You have to, if you want higher power or more thrust, you have to just make it bigger. You can't keep it the same size and try to get more thrust because the space charge limitation in the grids. So if you wanted to go to 200 kilowatts, you couldn't put it in the launch vehicle, or you'd have to deploy it, so it gets very heavy. So this is very good for low power operations, but when you want to move up to the 200 kilowatts for cargo missions or higher, this will run into some problems. Hall thrusters have been used mostly in Russia over the past 30 to 40 years. They've been flown up to 4.5 kilowatts. They're 60% efficient. Their lifetime is generally limited to less than 1 year. On the ground, NASA has picked up these and tested them up to 50 kilowatts and designed one to work up to 150 kilowatts. The efficiency is pretty much going to be set at 60%. There's not a lot that they can do to improve that. The lifetime, they claim they can go higher than 6,000 hours, but no testing has been done to prove that. So their lifetime is limited to 10 months or so. NPD thrusters are like VASIMR, a very high power device. They have not really been flown like VASIMR. There's only been one test. It was a quasi-steady, which means for 100 microseconds they would turn on the pulse at 700 kilowatts and then turn it off for a whole second. So the average power was about 400 watts. So it never got hot. And the efficiency was really, really good, which means it was eroding away the electrodes themselves. So it proved that it made thrust, but the results for performance are kind of up for grabs. These devices can work. They are 30 to 60% efficient in the lab, but their lifetime is limited by the erosion issue. Right now, hundreds of hours is the highest people have really reliably reported. And to go higher than that requires adding stuff to your propellant to coat the surfaces so they don't erode as fast. Go into details on that if we had more time later. So the unique VASIMR capabilities are it operates at high power, hundreds to tens of megawatts. The only thruster that's capable of that is the NPD thruster. It's 50% efficient or higher, which is average for electric propulsion device. And its lifetime, which I haven't gone into yet, should be very, very high. We have not tested for many hours yet, but we are an electrodeless rocket. We have antennas that are outside of the plasma and are shielded with an insulator, and the insulator can be very thick. So the plasma is pretty far from our antennas and would have to erode, a centimeter or more into it before it would stop working. And so we believe that our device will last a long time. And it turns out that our device is pretty efficient even if we pull the antennas far away. So we think that we can, if we need to get a long lifetime, we can sacrifice a little bit of efficiency and still get a long lifetime. And the other thing I haven't really mentioned, I'll go into in a minute, is constant power throttling. If you have a solar array that puts out 200 kilowatts, the VASIMR can take that 200 kilowatts and produce either 4,000 seconds or 6,000 seconds or 8,000 seconds ISP, and use all that 200 kilowatts. It can adjust the power ratio between the plasma generating mechanism and the plasma accelerating mechanism in such a way that we're using all the power to get the ISP that you want. No other rocket can do that. And because of the missions that I mentioned before, in the 200 kilowatt to megawatt range, NASA or those other private entities should want a VASIMR sometime in the next few decades, and why we are continuing to work on it and hope that are interested in our project.
What's the equivalent thrust in pounds that you get with those whole VASIMR, I guess?
200 megawatt or 200 kilowatt VASIMR is about a pound of thrust. So about
thrust?
yeah.
So it's just for deep
Right.
launching.
No, all electric propulsion devices must be used in space. They require a very low density background. So you can never, the thrust to weight ratio will never be greater than 1, and they will never work on the ground. Yep. So some of the VASIMR design challenges that we're working on right now at Astra, one is the waste heat management. Even if the rocket's 50% efficient, which it is, half the power is waste heat, and that's 100 kilowatts of waste heat, and the device isn't that big. It's it's a few tables. There's like 4 of those tables in size, and we're trying to get rid of 100 kilowatts of waste heat. That's mostly what I do at work all the time, is try to figure this out. I can't go into the details of how we do that. That's one of the key proprietary things, but basically we're trying to get it out passively without affecting the RF, because you're trying to transmit RF through this very hot region without it getting absorbed in the material and without causing reflections. So it's one of the key engineering problems that we have. And of course, you're in space. The only way to project it is with radiators, so you want it to get as hot as you can let it get to radiate into space at maybe a few hundred degrees Celsius. And that's a design challenge, to use materials in space at that temperature. Other design challenges are RF power generation, efficient coupling to the plasma. We operate in the RF frequency somewhere between 100 kilohertz and a few tens of megahertz. We've worked on solid-state RF generators with a company in Canada. I'll show more of that in a minute. And then you have to get the RF from the generator to the plasma. So we've developed a matching network and RF transmission system, and that's worked out very well. And we're very happy with progress on that. We have superconducting magnets. In space, you don't really want to waste a lot of energy making a magnetic field. And since the superconducting magnets exist, we use almost no energy making the magnetic field. You have to waste some energy cooling the magnets and keeping them cold in space. And so we're working on developing that system to work on our rocket. And of course, overall performance, we need to prove that we are over 50% efficient, have a long lifetime, and that the plasma really does detach in the VX-200 in our new facility. And we can do that for the first time because we're at our new facility with our huge vacuum chamber, and I'll go into that. To put some technical stuff into the talk, I added a model of the VASIMR efficiency. This is the equation for the efficiency. There's 2 main terms. One is for the first stage. This is EI, which is ionization energy, cost EV per ion. And I'll go over that in a second. And this is the kinetic energy of the ions as they leave the system, so basically the jet power. And the second term is related to the second stage, which is the acceleration stage. These are just the efficiencies of the different parts of the system. The DC power comes in, say 200 kilowatts, and we can split it whichever way we want, and to go into the ionization or the acceleration side. The RF generator is solid state and light, and we know that this generator is about 92% efficient. And it then couples to the plasma through our helicon antenna. And in the VX-100, about a year and a half ago, we measured the ionization efficiency, and that was less than 100 EV per ion. Our goal was 100 EV per ion, and we beat that. And with the with our superconducting magnet, which we'll have in 6 weeks for operating, we will beat that by a lot more, I hope. So we have this term nailed down. The second side is the acceleration side, or ICH booster side. We have another RF generator here. We know this efficiency is about 97%, so we're very happy with that. We have another antenna RF coupler here. Power that's transmitted from the generator to the coupler. Some of that power gets lost in just I squared R losses in the transmission line. We're figuring out how to optimize that, and we're above 95%. And then the antenna is coupling to the plasma, but not all of that coupled power is going to end up in the ions in the perpendicular direction. Some of it's going to be going into the electrons or in the wrong direction. And we don't know for sure what that number is. Some measurements are showing pretty good, but we're around 80% is what we're aiming for, and that seems to be reasonable. Then the final efficiency is the nozzle efficiency as the plasma expands out on the magnetic field lines. It's going to diverge a little bit as it comes out, or there'll maybe be some turbulence. Something will not make it a perfect nozzle, and we don't know what that number is. We're hoping it's around 95%. And so that's these terms here. As you change the specific impulse, the energy in the exhaust up, you can see the efficiency of the rocket increases to about 70%, 65, 70%. And this low region here, this is where it's dominated by the ionization losses. So basically in this region it's a low specific impulse. So you're putting a lot of gas in, you're just ionizing it, and it's just dribbling out the back of the rocket. You're not really getting much acceleration, so it's not very efficient. As you increase the power in the second stage, the dominating term becomes all the little efficiencies in the acceleration stage, and in terms of this part of the curve. So we're trying to operate right in the knee area, which is 4 to 6,000 seconds, which is where low Earth orbit stuff and going to the moon is really, that's the optimum ISP for that. Later. And these numbers are kind of pessimistic, so we think they can easily meet 60% efficiency at 5,000 seconds. So in 2007, we made a lot of progress on making some measurements. This is the VX-100, the precursor to the VX-200. This was just a copper coil magnet. Here's the helicon, the first stage. Then there's the choke coil, and then the ICH coil. You can see we have argon plasma operating inside here. This field strength is 60% of the design field strength for the VX-200. Just couldn't get enough copper to make the copper coils big enough, and we didn't have enough power supplies to power them anyway. So we made a lot of progress at 60% of the magnetic field. We measured the performance, that EV per ion, we got 80 EV. In the exhaust, we put a flux probe. So this little arm here has 10 sensors on it that collect the plasma, the ions as they come into contact with it. And as it moved across and swept like a windshield wiper across the plasma, we measured the plasma or the ion current, noted by the color here. And after we know how many ions we put in, so we get in the power, we got the EV per ion of 80, and we were pretty confident in this number.
When you're like if 200 kilowatts, you get 1 pound of thrust. If you have like 2 megawatts, can you get 1 pound of thrust?
If you have the same ISP, yes, the ISP is the same as the. Again, here's a cool video of the VX-100. This is the chamber on the end. It's a pretty small chamber. It's like 5 feet high and 7 feet long. The VX-100, as I showed before. Here's some plasma coming out. This is one of our probes. It's a reciprocating flux probe. It just goes up and down the center line. That was a different flux probe there. And here's the windshield wiper flux probe moving across and collecting the plasma. You can see the plasma trapped on the field lines there by the probe. Then we put a paddle in there and let it hang on a swivel, and the gas pushed it that much. It's pretty impressive how much force we got. This is a smaller paddle. You can see when the gas turns on before the plasma even ignites, the pedal is moving. Then we turn on the RF, and the plasma moves even further. So we do produce a decent amount of thrust.
In a relative sense.
In a relative sense, yeah. You can see it on the paddle, which is pretty cool. Most, with an ion thruster, you would never see anything like this, so it's pretty cool. So we proved that force target works. You can see on this chart, this is time. As we turn on the pulse, what we do is we turn on the gas, then we turn on the RF in the first stage, then we turn on the RF in the second stage. And in the VX-100, that took about 2 seconds. The flow rate is this purple line, and that's a couple thousand SCCM. the force target is moving a little bit. Just because the gas is on, it's measuring a force of about 0.7 millinewtons. When the helicon comes on, which is the red line, it moves up to 12 millinewtons. And then the black line is when the ICH, the second stage, comes on, and it moves up to 30 millinewtons. Remember, this is a small target in the center of the plasma, so when you integrate that out over the whole plasma, we got a total force of 810 millinewtons. This probe was validated at the University of Michigan. One of our postdocs went up there. He took that probe and put it next to a Hall thruster in the plume of the Hall thruster, and the Hall thruster was sitting on a validated thrust stand that's known throughout the electric propulsion community as being one that works and everyone believes. And we put our probe in the plume, and we moved it around, and we did all the analysis, and they matched within 2%. So we know that putting that target in the plasma is a valid way of measuring force in thrust. So finally, on to the VX-200, which is what we've been working on at Astra for 2 years now. We moved into a new facility in December of '07. We spent most of '08 getting the facility up and running. We got a new vacuum chamber. And then on top of that, we were building the VX-200 from scratch during that time. The goal of the project was to operate at the full 200 kilowatts of power, to measure the performance, to operate with a superconducting magnet since we weren't experienced at that, measure the ionization cost with the full field, and measure the heat loads on thermal components so we can design the thermal system to work in space. I have a better picture of the VX-200. So thermal management, basically this is the helicon section. This is the internal surface. It's a cutaway view, and it's kind of squished, so I don't give away the exact proportions of the rocket. But the antenna is in this region here, wrapped around it. Plasma, neutral gas comes in here, is ionized under the antenna and comes out. It's fully ionized here. The waste heat makes it to the wall, a lot of it through radiation, and the rest of it through some sort of plasma surface interaction. We don't know what the ratio is for sure, because we don't have the full magnetic field strength yet. But anyway, we got to get that waste heat out from this surface all the way out the end of the rocket without getting the magnet hot. Because right here is, in our VX-200, is a 4.5 Kelvin magnet, right, about 30 centimeters away from the plasma. And in the real rocket, it's closer. So we really have to figure out how to get the heat out without damaging the magnet or risking the magnet. And also the antenna has to transmit through it. You know that the hotter ceramic or any material gets, the more lossy it is to RF. So basically, if you let it get too hot, it'll just absorb all the RF, and we won't have a plasma. We'll just have a cooker for the ceramic. So it's a tough problem. And of course, it can't weigh very much. So anyway, that's what I do most of the time, and unfortunately, that's all I can tell you about the thermal problem. The next problem is the superconducting magnet. To get one to work in space, we decided to go with the space operating one will have a high temperature superconducting magnet. High temperature means 40 to 50 Kelvin in this instance, with a peak field around 2 Tesla in the choke coil. The 40 to 50 Kelvin works out because there's cryocoolers that you can buy off the shelf that will work at 40 Kelvin and in space, they claim. So we're going to work with building a magnet that works at 40 to 50 Kelvin and has to survive launch, which only AMS has attempted to do with a superconducting magnet before. So we're going to try. We have to learn how to build a superconducting magnet to survive launch. We have a low temperature superconducting magnet in the lab right now. This is the outer shell of it. Inside there is the coils. It was manufactured by Scientific Magnetics, who's making the AMS magnet, which is going up on space station maybe at the end of the shuttle program. It might be the last mission. It operates at 4.5 Kelvin, and basically it was a huge lesson in how to build a magnet, and what to do and what not to do. And Friday I installed it in the engine bus in the rocket. So hopefully in about 6 weeks everything else will be installed and we'll get some results. The RF generator is one of the other technical issues. Nautel Limited is a company in Canada, and they built the amplifiers for us. We gave them the specifications. We wanted something light, compact, efficient, and solid state, and they did a perfect job. And this unit here produces about 48 kilowatts of RF power. You can see it's not very big. And this unit here, which is only slightly bigger, it's only about 6 inches taller, produces 165 kilowatts. And we know the efficiencies of those, as I mentioned before, 92 and 97%. So we're very happy with that. And they're helping us work on making them vacuum qualified and space qualified things. And one of the keys is we managed to get this to match the plasma. At high power, not very many people have matched solid state amplifiers into a plasma before. With the interim magnet that we were working with over the last 6 months, we did get it to work. So the interim system that I just mentioned, basically the magnet that we ordered from Scientific Magnetics was a little late. It was almost a year late. So we had to do something to test out as many systems as we could in the meantime. We made this interim magnet. We had a mandrel. We wrapped 1/4-inch tubing around it so we could power them with our power supplies that we had, and started testing everything we could test. Unfortunately, the field strength was only 5% of the design because it was just regular copper tubing. It had a lot of joule heating losses, so that was our limit, 5% of the magnetic field. But it allowed us to get the RF generators coupled to the plasma. We got them running at high power. It proved that we had good RF transmission. We didn't have any arcs in the system that weren't supposed to be there. We got the control avionics all working in the vacuum chamber without overheating. We got the propellant to P system to work reliably. And we proved that our diagnostics and our new facility was working as well. So over the past year, although we didn't get the VX-200, the full system working, we proved almost everything else. And we're just getting ready to do the final test in the next couple of months. From the outside, you really couldn't tell if this was the VX-200i or the VX-200. The magnet, interim magnets, is in here, and just this is a mock-up that we made to help us assemble the VX-200 and get an idea of how it would look like. It turned out it was very handy. We made that into the interim magnet. So you can't see the coils in there. It looks just like the regular magnet. This side, there isn't that much interesting on it. This is the ICH end. The plasma comes out of this nozzle. These are some diagnostics here. The helicon, the first stage RF connects up in here. This is a picture of it inside the chamber. The chamber is 14 feet in diameter and 33 feet long. This is the front end. The helicon power comes in. Matching network is under this cover, so it matches the impedance of the plasma and goes into the helicon section. The ICH section is this. The ICH power comes in here and is coupled through this box into the plasma. And then we just have other avionics boxes on the side. You see the water lines to cool the magnet are there. We have a plastic wall because we're pumping in a lot of gas. You can't pump it out and keep the pressure around the antenna or around the rocket low. So we actually divide the chamber into 2 halves with a plexiglass wall, and we have separate pumping on each side of the chamber. And that's what that reflective surface is. Which is a big picture of the chamber. Again, 14 feet in diameter and 33 feet long. And we got it delivered. Well, we moved into the building in the December of 2007, and the chamber is now working very well. It gets down to 3 × 10⁻⁸ torr in a few hours, and we actually are going to increase the pumping to 100,000 liters per second in the next couple of weeks. See, also we have a nice diagnostic setup. Downstream of the rocket, we have this translation stage that moves 5 meters along the axis of the rocket and 2 meters left and right. There's a little table on top where we have a bunch of probes to measure plasma properties in the plume. Prove that those work over the last few weeks. You can see that this is a magnetic field map. The field lines won't touch the side of the chamber for many meters, about 3 meters. So the plasma will have a long ways to travel before it interacts with the wall. This is one of the few chambers in the country where you can do this with electric propulsion. And we should be able to definitively show that the plasma does detach and show what the performance of a rocket is in this facility. Some of the probes that we have RPA, that's the tip of the RPA there. We have the force target. This is a bigger one because we generally are further away from the rocket, so it's okay to put a bigger force target. I think it's about 15 centimeters. There's a stationary flux probe array, so there's little collectors there, and there. And then there's a guarded flux probe here, and we move that around and characterize the plume throughout the entire volume.
Do you have any magnetic field coils?
We do. Not on there right now, but we do have one. It's a 3-axis magnetometer, high frequency. The recent results, we got 149.2 kilowatts of RF power coupled into the plasma. So even with that really bad magnetic field, we got almost 150 kilowatts into the plasma. With this rocket and the solid-state amplifier, we are changing the time scale a little bit. The VX-100 was 2 seconds. This one takes us closer to 10 or 12 seconds to get it running. We turn on the gas, which is the green line, and we ramp up the helicon power, and then once the helicon power reaches its limit, which is 30 kilowatts is what we're designing it to work at right now, turn on the ICH and it just jumps right up to 150 kilowatts. And then so here's some images. I didn't make that plot up. We did actually have some plasma. This is, without plasma, this is what it looks like kind of from the side through one of our side viewports. The 30 kilowatts, helicon only. You can see the plasma coming out. The next picture shows the field line following a little bit better. This one here is 148.5 kilowatts in the booster section. It's really, really bright. The plasma's coming out, and we're not actually ionizing, or we're not heating the ions. We're heating mostly the electrons. Because the field strength is so low, we're not coupling to the ions. We're basically making another helicon in the second stage and just heating all the electrons in the area. So it gets really bright. There's some different images with slightly less sensitive camera settings, so you can kind of see the field lines, the magnetic, or the plasma following the field lines here. When you turn on the second stage, you can see the field lines still, and then there's the extra glowing on the outside, which is probably that ICH power just coupling the electrons anywhere it can find it. Here's just a movie of the firing. This is the helicon section on, but it takes about 10 seconds. Right when the ICH comes on, slower speed just for the ICH portion of the firing. It gets bright, and then there was that drop off, and it finishes. So, the VX-200 so far, those are the results, the recent results for those pretty pictures, and the high power. The magnet is being installed now, and we'll have the VX-200 running in a few weeks. Our next project is to work with NASA. We have a space act agreement with NASA to attempt to put the VASIMR on the space station, 200 kilowatt version of it. And this is the P3 truss on the top of a cast site. We can mount the VASIMR to it, and it will have 2 rockets. Each of them will operate 100 kilowatts and try to fire through the center of gravity of the space station. We have some radiators to get rid of the waste heat from the cryo coolers that keep the magnets cold and the electronics. This is basically our first conceptual design of the space station.
Would it be used for altitude or correction?
This is just a demonstration of the technology. Right, because of where we're putting it on the space station, we can't do anything useful. We're actually firing perpendicular to the orbital, to the plane of the orbit. Until we prove that it works, NASA doesn't really want us to try to adjust the orbit of the space station. They want us just to do a technology demonstration first. Of course, we want to make it so that if they do change their minds, we can read it and boost the space station. At 200 kilowatts, you have to fire a small fraction of the day to make up for the drag. I think it's like 6 hours a day, I think, to the space station.
It's pretty clean burning.
It's just argon. Argon doesn't react with anything around space station. It's much better than the oxygen ion environment that it's in.
Project actually funded?
This is all at Astra Rocket Company project so far to do all the engineering of it. There's a Space Act agreement where NASA is committed to work with us to be a pathfinder for this. The space station is a national lab now. They're supposed to be able to put research projects that are of national interest, and this has been designated the pathfinder for that. And NASA is supposed to work with us to get this on space station and take some of the burden for the certification and integration cost. But right now, it's very high level.
But you would build and own the hardware?
Yeah, we would build all the hardware, except for what we buy from NASA. Like this gimbal here is NASA furnished hardware, but most of it would be ours.
Is it appropriate to say that you do maintenance and repair?
No, because Franklin Chang Diaz is the president of our company, and he's a former astronaut, and he loves maintenance and repair. He wants everything on this to be able to be pulled out and replaced. So it's called an orbital replacement unit. So he wants the RF generators to have handles on them and little connectors, so you take them out and you throw away the bad one, and you have a new brought up and you replace it. So
Well, if you had this as an orbital transfer vehicle, reused multiple times, what do you project as the number of reuse? How much maintenance would be required, and how would you accomplish that?
if things went the way they're supposed to go, and we do get the 10 to 30,000 hours of life that we need, we really shouldn't have any maintenance. If you were to do maintenance, you would have to pull out the cores of the rocket and just replace the cores because that's where the erosion would occur. The amplifiers should stay the same, you know, the propellant system.
Concept for that maintenance robotic, or would require, or is the concept gone that far?
It hasn't gone that far. I do not know the answer to that. It would probably be robotic for orbital transfer vehicle, I would imagine. But I think the thing that would go first, we'd hope to design it so that the solar arrays would degrade first, because you can't do anything with those. They degrade beyond use. You just throw them away and use new. Kind of design the system so that it lasted as long as the solar arrays, and then just ditch the whole thing and start over.
Do you have a concept to use a nuclear reactor for power rather than solar arrays?
No, we don't. We at Astra can't afford to do that. If NASA were to develop a reactor, we would gladly develop a 12 megawatt VASIMR system to go to the moon or to Mars. Matter of fact, if you use 12 megawatts and you go to Mars, it only takes 90 days with the VASIMR system. So we would gladly develop a system for that.
Do you have a concept for life of your solar arrays might actually be?
I don't know. I don't know the answer to that.
You could make on one set of solar arrays?
I can get back to you on that. I know there's a guy in my company who knows that answer.
I want to ask a question going
Yeah.
back to, you were saying it'd take maybe 6 months to go to the moon. What if you use this like in a hybrid mode, where you use maybe get some solid rockets to start your journey to, but you know, small enough so you build a big rocket, and then just take over with the acceleration, constant acceleration, once you get that started. I mean, is that a possibility, so you don't have to wait to still use the set technology?
Yes, you could definitely do that. You could do it so you launched into, rather than low Earth orbit, you could launch into highly eccentric orbit, and then just turn on the rocket after that point. I don't see a reason why you couldn't do that.
You have a slide with the forward plan, like what the next milestones and the dates are. Is there a tentative date on putting it on the ISS? Is there? I know you're saying the next 6 weeks we're going to go find data with 200. But I mean, after that, what's the plan?
I do not have a slide with that, actually. I just have more pretty pictures. The plan is to take data for quite a while, actually, most of the rest of the year, to figure out exactly how efficient it is to get the power ratios worked out the way we want. It'll take us about a year to do that. And we have, our company plan is to put this on space station in the year 2013. So we'd have to get it fully, from the end of this year, when we have all the data to build it, we would have about 3 years.
So it took a full year to build 200i, since you have magnitude data. So now you're going to be testing it for a year.
Yeah.
All right,
About 6 months, yeah.
So then from 2010 to 2013, you're building and testing.
That's a tight schedule. Right now, our company is
Yeah.
very small. We're less than 30 people between the United States and Costa Rica. We have a Costa Rica facility too. If the NASA space station project goes forward, our funding would have to increase to meet that schedule. Hire a bunch of people to make sure we can do it.
So, also, what is the source of funding? I realize you said for getting on the ISS, you basically have to get funded by NASA to be.
NASA wouldn't. Yeah, our hardware and the development of the VASIMR would all be from private funding. Only the integration with space station, for like the safety issues and how to get it from transfer vehicle to space station, NASA would help us with that, because there's a lot of paperwork to get anything on NASA, on the space station.
So, and when it comes to private funding, how are you pulling off where you have to convince somebody to invest in a project that's not going to mature for another 10 years?
That's a very good question. Our Franklin Chain Diaz is a very persuasive guy. And he goes around and basically talks to people who are really wealthy and really have a long-term vision, and they're willing to invest money and not see a return for 5 years. So it's not like a normal investor, a venture capitalist. They wouldn't invest in our company because they want money in 6 months or a year. We're more like an angel investor, where someone really has a long-term vision. Franklin just goes out and talks to them and asking for more money. Now, if this project matures and we get closer to going to space station, then timescale decreases and we'll get more people interested in getting a return faster.
Just like the FAA imposes launch requirements on but you don't launch, so you just operate in space. Are there any governmental entities that kind of put strings on your devices?
I don't think so.
Vibration tests and shock tests, things like that.
Yeah, but that's usually your launch vehicle, and NASA will require that just to make sure it doesn't fall apart during launch. And when it's on space station, it doesn't break it off and fall away. I think there's a few UN treaties about leaving stuff in geosynchronous orbit and stuff like that, but there's no real laws restricting what we do.
Probably helpful.
Yeah.
Also, with regard to testing on the ISS, why does it need to be bolted to the ISS to be tested? Why can't it be tested on it? Where there's no, obviously, if anything unforeseen happens, back to a vehicle that's going to have 6 as opposed to if you stick it on a satellite, any orbit, a less eccentric orbit than 50 degrees, something nice, equatorial, that's unmanned, so do whatever the heck you want.
That's a good question. Most of the answer is NASA is a very high-profile place to put this rocket, and we believe it's very safe. On the space station, most of the burden is just to make sure that we follow the safety guidelines, but there's nothing that this thing can do to really hurt space station.
Well, I would also think it's because of the power restriction too. Because I mean, if you if you need 200 kilowatts of power, and you're putting something in orbit, I mean, there aren't very many places in orbit you're going to find 200 kilowatts laying around outside of the international.
I don't think you'll get that from the space station.
100K.
You could probably.
Well, the space station is 100 kilowatts, but we're only going to operate for 20 minutes, 10 to 20 minutes with batteries. We're going to trickle charge them and operate batteries because NASA won't give us the full space station power. So we get about, the maximum is 3 kilowatts, I think. So we trickle charge the batteries and then fire full power for 10 to 20 minutes, depending how much mass we have for the batteries. The problem with doing a free flyer is that we'd have to develop a whole spacecraft that could control itself and do guidance, and that is a problem we didn't want to deal with. We wanted to just build a rocket and then use a NASA transfer vehicle to get it to space station, hook it up, and then test it. And if something goes wrong, we could replace it. If we do a free flyer, something goes wrong, that's it. We got to launch another one.
Could the NASA transfer vehicle be your base though for the test?
You ask a lot of very good questions. There's one of the COTS vehicles is there's SpaceX and the other company.
Orbital.
Yes, Orbital. Their vehicle works out very well. We're thinking of keeping their transfer vehicle attached to this and either flying away later or keeping it on here and using that as our control vehicle. And that's a possibility.
So you would take it up on that orbital transfer vehicle and test it on the space station, and then maybe turn it into a functional
Free flyer.
vehicle for small payloads or something like that
Yep.
to the moon. So your first test vehicle may very well be your first operational vehicle.
That is one of the options on the table right now. We're very early on in the spaceflight design process, and our company motto is basically keep everything on the table as long as possible. So we are considering that.
All goes as planned.
Yeah, if things work well, yes.
Electromagnetic interference.
We don't believe it's very much. The plume will produce a region where you can't look through it with the KU band antenna, but it's pretty small. It's only a few meters long and a couple meters in diameter, well, maybe like 10 meters long, and it's pointing away from the antennas anyway. It's something that we've already thought about. The S-band antennas, the volume is bigger, but it's still generally out of the way. The wavelengths that we're dealing with don't broadcast. Like a broadcast antenna that generates RF waves, we are too short for that. Our system's too short to broadcast waves. We might generate noise that feed back onto the structure, which we're going to deal with by basically grounding and shielding and figuring it out. But we don't think it'll be that big of a deal. I only have an anonymous slide left. I really only did a fraction of this work, of course. Most of my co-workers did a large portion, about half of the team for our chamber. But I still would take any more questions.
When Bigelow puts up his space hotel, could your vehicle with the orbital system be used as a booster?
Yes, it
Would you
could.
need it?
It would be very helpful for Bigelow. If we used our rocket, say 200 kilowatts, and Bigelow's hotel could be at a lower orbit, because our rocket could fire all the time at 200 kilowatts, and it could make up drag in this, even at a low altitude, like 100 250 kilometers. So it would be easier for them to launch people to the hotel to make money because it'll be at a lower orbit. They can launch more people on each time, and we just save them propellant and fire.
We're going to get the 200 kilowatts from the lower orbit with a solar array the size of 4 football fields generating that bag.
So we might have to go a little higher than that. But yeah, there's an optimum that's actually lower than you would think. The drag on the solar arrays is less than on the space station. The total drag is less than 0.7 newtons, even at the worst time of the year. And the 200 kilowatts, we're making 5 newtons. So we're easily going to make up the drag. But we got to talk to Bigelow. He's a recluse, and we haven't really gotten to talk with him yet. We would love to work with him.
Going back to the comparison of chemical versus this VASIMR or ET in general, just look at ISP alone. That's really kind of a snapshot, right? It's just a propulsive element. It doesn't include all the tankage and all the feed system and supply system and heat rejection and all that stuff.
Right.
So I wanted to get a feel from you, say, let's say you had a chemical propulsion package that you could plug into something for some purpose, for some delta V purpose. Let's say you wanted to provide 500 feet per second of delta V for a certain amount of mass based on chemical propulsion package versus a VASIMR package. So from what you showed so far, it seems like, we know what a chemical propulsion package has to have with it. Oxidizer and fuel tanks and avionics and gimbal maybe and, whatever. But with all the stuff that you have on the VASIMR, which is these coils and containment, for plasma, et cetera, you really get you think you get a sufficiently tight package, low weight package, that you don't essentially, take all the ISP advantages that you have, but you lose them in the integration and the engineering of it into a module. Have you done an analysis or study that sort of shows that trade against a chemical?
But
Maybe
the trade, unless you're doing very small changes in velocity, almost always win with electric propulsion. If you're doing even something simple like north-south station keeping on a geosynchronous satellite, with the chemical propulsion, you have your thruster, chemical thruster is just going to be basically a little container with a nozzle. But with electric propulsion, like an ion thruster, it also weighs about the same for north-south station keeping. And the power supply unit is about the same size. So
Really?
it maybe weighs about twice as much, but you save 10 times as much propellant.
and that's kind of what I'm getting at. If you have a 1 pound thruster,
Yeah.
or a bank of 1 pounders with the feed systems for it,
You almost always win. If you're in orbit already, you almost always win with electric propulsion.
with electric propulsion,
Yeah.
with proven electric propulsion. Well, how about with a VASIMR?
Oh, with the
Because you
VASIMR,
still have to package it to the
I don't know where the delta V line would be. I don't know. It would be somewhere less than probably a kilometer per second is where you would trade off with chemical propulsion because of the magnet weight of the RF generators. I'd have to go through and do a study, but most missions where you're trying to do something interesting would win with I'd have to sit down and do the calculation. I have a slide that would show that, but most missions you would win. Because the VASIMR alpha, the power or the weight per unit power is not much higher, maybe a factor of 10 higher than an ion thruster, which is not that much. It still weighs very little.
But it's not really been demonstrated yet. I mean, that's the big risk, right?
Right. Well,
You may not know what you don't know.
Right. Well, we're getting closer to narrowing down what the alpha number is. Like that one chart that had 2, that number is starting to look a little less realistic. 10 is starting to narrow down to 10. So that seems to be a number that's reasonable.
Maybe you start off comparing with the ZIPS system, right? Xenon Ocean, that would be
Yeah. I haven't looked at that stuff
Because
in a while.
chemical propulsion is kind of a little bit of a different beast, but if you were competitive with a ZIP system, then you're in the game.
Yeah.
And if you're not competitive with a ZIP system, then you're not in the game.
Well, for zips, I wouldn't try to put VASIMR up against an ion thruster. The application for an ion thruster is lower power with about a year north-south station keeping or something less than 50 kilowatts. VASIMR will lose compared to the ion thruster in that range because the efficiency and the ISP, it won't work. VASIMR is good at 200 kilowatts and above. That's where I would really say that almost nothing can compete with it, 200 kilowatts and above.
Is there an upper limit, you think, that where it just becomes too inefficient because of all the coiling and, other...
The real issue with getting bigger is the heat rejection. You can make the magnets bigger, and you actually would gain as far as density that way, but then you're putting more power into this slightly bigger volume with the surface area that's not growing fast enough to get the heat out. So it's really the upper limit is going to be getting the heat out of the system. And I don't know what that number is going to be. My guess is first iteration, 500 kilowatts, you could probably design something reasonable. Second or third generation, you'd be in the megawatts.
So have you looked into like recycling some of that waste heat to anything else?
Not looked into that yet. We could try to recycle it back into electricity. We haven't looked into that yet.
My name's Alex Munchak. I'm, of course, as a continuing education student. The role of NASA is to develop and demonstrate technology, which then they can transfer to industry. So you're an example of that. Can you explain a little bit about how that was done and where the documents are located of that NASA's demonstrated technology, and where are you publishing the results you find, or how does this process work? And have you seen it anywhere else being done like this?
That's a good question. I don't know the answer to all of that. Basically, we were the ASPL at NASA, Advanced Space Propulsion Laboratory. Franklin decided to take it private when the funding for electric propulsion was going down at NASA, and he thought he could make. He signed a Space Act Agreement, which is the way that private companies can work with NASA. In that Space Act Agreement, we got the patents for the VASIMR, and as long as we keep developing the rocket, we can have the patents. We continue to work on new Space Act Agreements with NASA to get on the space station and to move forward our relationship with NASA. I don't know. Do you know any more than that, John?
What were all the questions again?
Well, mainly the documents. Where does NASA publish the documents of their technology development, and where would you guys publish anything?
There's a technology transfer office,
Yeah,
which is now called the Innovative Partnerships Office.
Innovative Partnership Program, right?
You might also
The
check.
IPP is a program run out of headquarters, but all of the old technology transfer offices at NASA have been rebranded as Innovation Partnerships Offices, and the program is something separate. They collect these things. Space Act agreements and things like that, I guess, are public record. They're merely contractual documents that NASA signs with outside entities. And, proof of principle, the different laboratory reports,
Yeah, there's all
conference reports,
conference reports and journal
articles.
There's a ton of
If you do a literature search on VASIMR, on Franklin Chang Diaz, on Lenny Cassady, you should come up with these.
Right. And recently, the past 2 years, we've limited how much we've published because it's proprietary now. We're trying to make a profit on it. So there's not a lot that's come out in the past 18 months.
Some of the very early work you might collection here, look in the G Center Director's Discretionary Fund Activity. Franklin did some of that.
Is that all?
Okay, any other questions? All right, let's thank our speaker.